Yo, 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 everybody. Here's another video covering some of the things that you should be bringing over with you from Chemistry A into Chemistry B. Specifically, today I'm going to talk about compound nomenclature, everyone's favorite or maybe least favorite thing that they learned in Chemistry A. We're going to talk about ionic compounds, covalent compounds, and acidic compounds, and how to write names and formulas of all three of those things. Now, one of the first things that might be helpful for you to familiarize yourself with, if you haven't yet, is where the metals, metalloids, and nonmetals are on the periodic table. Because depending on what combination of these things you have bonding, that's going to determine what kind of bond is formed, and therefore what kind of compound is formed, and therefore what kind of nomenclature rules you're going to use for the name and the formula of that compound. Now, I do want to point out that it's not really this simple. Bond characteristic is really based on electronegativity differences and what electronegativity difference exists between the different things that are bonding. So if two elements have certain, remember, electronegativity is how strongly things are pulling electrons towards themselves. So if one atom, for example, is pulling electrons towards itself much more strongly than the other atom in a bond, that might result in an ionic bond where an electron actually changes ownership from one atom to the other. Whereas if they have a more similar electronegativity where two atoms are bonding and they both have a similar pull on electrons or similar electronegativities, you might end up with something more like a covalent bond where an electron ends up being shared between those two atoms. But remember that electronegativity is a trend that you can track on the periodic table. And so therefore, what tends to happen is that if you can remember where the metals, metalloids, and nonmetals are, and you know what the different things in the compound are, you can follow a couple of simple rules to tell you what kind of compound they're going to form. So, you know what? We're going to do this Dora the Explorer style. And if you have, I'm going to stop after each question and give you a chance to answer. So, first of all, if we have a metal and a nonmetal forming a bond, what kind of bond is that going to form? That's right, everybody. That's going to form an ionic bond. Good job. Now, what if you have a nonmetal and another nonmetal trying to form a bond? What kind of bond is that going to form? That's right, a covalent bond. Well done, everybody. Now, one of the biggest things that everybody struggles with is when you look at some compound written on a piece of paper or on the side of a bottle, how do you know what kind of compound it is and therefore what rules to follow? So here is my advice. Look at the first thing in the compound. Look at what it starts with. If that compound starts with a metal, you're dealing with an ionic compound. If the compound starts with an H or has an acid in the name, then you're dealing with an acid. And acids are kind of like special ionic compounds in a way, but it's a little more complicated than that. Now, if the compound starts with a nonmetal that's not hydrogen, or if you see prefixes in the name, you're dealing with a covalent compound. Now, if you're dealing with an ionic compound and you want to write a name for an ionic compound, here's what you do. You're going to first name the cation. Remember, cations are the things that form positive charges. And it's very simple. It's just the name of the element. Or if it's a polyatomic ion, meaning an ion made of multiple atoms, you're going to look that up and just use the name of that polyatomic ion. Now, some of you maybe have the polyatomic ions remembered. Most people don't. If you don't have them remembered, you can use, and you're in one of my classes, you can use the chemistry survival guide that I gave you. And if you don't have that with you, I'm going to put a link to that in the description of this video so you can download and print out or just look at that Google Doc. Now, if the cation is a transition element, remember those things can have different oxidation states or different ionic charges. So you need to use a Roman numeral in parentheses following the name of that element to indicate what the positive charge is. That's how you write the first word of the name. The second word of the name is the name of the anion. If it's a single element, you're going to take the root of that element name and then just add "ide" to the end, or not add "ide." You're actually going to replace the ending of the word with "ide." Or if it's a polyatomic ion, you're just going to use the name of that polyatomic ion. It's very simple. Let's do a couple examples. So I'm going to pause for a few seconds in case you want to pause this video and try these out, and then I'll walk you through how to do these. So did everybody pause and try these out? I sure hope so, because here are the answers. The first element is calcium phosphide, because Ca stands for calcium. And so to name the cation, you're just going to use that name. It's calcium. And then phosphorus is a single element. So what you're going to do is take the root of that word, which is phosp. You're going to change the ending to ide. So you're going to take out the orus and change it to ide, and it becomes calcium phosphide. Now, this next element is calcium and phosphate. So since the cation is a single element, you're just going to write the name of that element. It's calcium. Since phosphate is a polyatomic ion, you're going to use just the name of that ion, phosphate. So it's just calcium phosphate. Pretty straightforward. Now things get a little bit more fun. Fe is iron and S is sulfur. So iron is a transition element, which means you've got to use a Roman numeral in parentheses to indicate what the charge of that iron is. And sulfur is the anion, so you're going to have to change the ending of the word to ide. So it's iron sulfide. But the question is, how did I know that this was a 2 here? How do you know that the iron has a 2 plus charge? Well, this is where it gets a little more tricky. You've got to think about what is the charge of the anion and what must the charge of the cation therefore be to neutralize that charge. So sulfur always forms a -2 charge, which means that in this case, if there's one sulfur and one iron, and together they have to equal 0, if the sulfur is -2, the iron must be +2. So it's iron 2 sulfide. Next compound, this is nickel and nitrite. Nitrite has a -1 charge, and there's 2 of them. So if there's 2 -1 charges, that means that this nickel must be a 2 plus charge to cancel those 2 negatives out. So it's nickel 2 nitrite. And then this last one, this is a fun one because ammonium is the only or one of the only positively charged polyatomic ions out there. So this is a double polyatomic ionic compound. But actually, they're really easy to form because you just use the names of the 2 things involved. It's ammonium and phosphite, so it's ammonium phosphite. Pretty simple there. Now, what if you're going the other direction? What if you are trying to write the formula of something that you know the name of? Well, it's obviously related to what we just talked about, but you're going to have to go the other direction. So here's how it works. The first thing you have to do is determine the charge of both the cation and the anion. Then you're going to find the lowest number of each of those things that combines in order to make a neutral compound. In other words, you want to have the same number of positive and negative charges so that they cancel out and make something with a 0 charge. And in doing this, you're determining the subscripts of the formula. And then you're just simply going to write the formula with the cation symbol first, the anion symbol second, and subscripts below each of them to indicate how many of each of those elements or polyatomic ions are there. Couple of things to keep in mind. Again, polyatomic ions are in that survival guide that you can find linked to this video. And transition metals are going to be followed by a Roman numeral to indicate their charge. Here's a couple examples. I'm again going to just stop talking for a couple seconds so that you can pause this video and give these a try. And here's the answers you've been waiting for. Oh, wait, I apologize. I didn't put the answers in a slide because I'm going to bring the camera back up. I'm going to maximize the camera, and then I'm going to switch over to my document camera so that I can walk these through with you by hand, because I think that'll be a little bit easier to show kind of what's going on in terms of determining the formulas here. So, step number one is determine what is the charge of each of your ions. So, if we were trying to write an formula for sodium chloride, sodium is our cation, and if you look it up on the periodic table and you remember those trends that we talked about in the last video, sodium has a +1 charge. And chlorine is always going to have a -1 charge. So how many of those things need to combine together to make something that's neutral? Well, you have a +1 and a -1. So if you just had one of each, that would make something that's neutral. So this is just NaCl. Now, sodium carbonate, again, we're dealing with sodium that always has a +1 charge. Carbonate is a polyatomic ion. Now, the clue there is that it ends in ate. Anything that ends in ate or ite is probably a polyatomic ion, and you're going to have to look on the chart. You're not going to find it on the periodic table. Anything ends in ide is probably just an element that you'll find on the periodic table. So carbonate is CO3 with a 2- charge. Okay, how many of those things need to combine together to make something that is electrically neutral? Well, we have something with a +1 charge and something with a -2 charge. So if we just had one of each, that wouldn't be neutral. We'd have too much negative charge. So what we need to do is have two of these, two entire sodium atoms bonded to one of these polyatomic ions. That way, we would have two pluses and two minuses, and they would cancel out. And the way to indicate that in the formula is you're going to put a 2 right there. Two sodiums and one carbonate make sodium carbonate, and that's electrically neutral. Now, these parentheses are technically optional, but I'll just go ahead and leave them there. Now, iron 3 oxide. So iron is Fe, and the 3 in parentheses tells us that it's a 3+ charge in this situation. It could be something else. That's kind of the whole deal with transition elements. There's iron 2, there's iron 3. There might, in some other instances, even be other forms of iron. So that's why the Roman numerals are essential for transition elements. But in this case, it's iron 3+. Oxide is oxygen, and oxygen always has a -2 charge. So how many of those two things need to come together to form something neutral? Well, this is a conundrum, right? Because if you have one of each, that's not neutral. If you had two irons, that's not neutral. If you had two oxygens, that's not neutral. So how many of each of these are you going to need to do? Well, you can go about this in a couple of different ways. You could either go kind of the long way and you could just start adding more of whatever you're short on until you get to something that is neutral. Let me show you that. So right now we have more positives than negatives. So if we just add another oxygen, now we still have a problem because now we have more negatives than positives. So if we add another iron, well, now we have more positives than negatives again. So let's add some more negative. And now we are even. We've got 6 plus, 6 minus. This is what it's going to take to form a neutral compound out of these two ions. So there's 2 irons and 3 oxygens, and the way that you're going to indicate that is with a 2 there and a 3 there. Now, that took a while. And you can imagine if you had to do this a lot, that would not be the most efficient way to do it. So, what you might have noticed is that there was a 3 plus here and a 2 minus here, and there ended up being a 2 here and a 3 here. The numbers switched spots and dropped into the subscripts. That is a move called the cross drop. So, you can actually do that anytime. You can take the charges from the two ions, switch them and drop them in the subscripts, and that will create a balanced equation. Now, the cross drop is also my favorite dance move. So anytime you need a new dance move, you're going to, hold on, you're going to do the cross drop, the cross drop. It's just what you're going to do. Now, tin phosphate, specifically tin 4-phosphate. To be honest with you, I don't know if this compound actually exists in real life, but you know what? You should be prepared for anything, not just if you're a Boy Scout. And you know what I'm always saying? You know my motto: a Boy Scout is just a future chemist with a handkerchief. I've literally never said that before. Tin 4 is SN with a 4 plus charge, and phosphate is PO4 3 minus. So again, this is a situation where it's not as simple as just saying, oh, we need one of each, or maybe we need two of this and one of that. We're going to need to cross drop these things. So if we take the 3 from over here, cross drop it down here, the 4 from here, cross drop it over there. Let me rewrite that for you. Then that should take care of it. That should be our balanced reaction. Congratulations, you just learned the cross drop. Okay, let's go back to the presentation now. That takes care of ionic compounds. What a doozy. Now we're on to covalent compounds. Covalent compounds, remember, are when two nonmetals are trying to bond together. And they're different than ionic compounds because electrons are going to end up shared instead of being fully exchanged. Covalent compounds, in a lot of ways, especially once you know ionic compounds, are easier than learning ionic compounds because the rules are the same. You're going to follow the same steps. You're going to use the name of the first element and then change the name of the second element to "ide," but you're going to add one more thing. You're going to add prefixes in front of each word to tell how many of each atom are there. So do you remember the prefixes? Go ahead and stop this video for a couple of seconds and write them down or see how many you can remember. I'll give you the answers in a second. Here they are. The prefix for 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Now, and I apologize, this is cut off by these tools. Note that sometimes mono is left out. Mono is not used if it's the prefix of the first word in a name. Also note that sometimes the last vowel of a prefix is dropped. For example, it's monoxide, not monoxide, right? So you drop the O at the end of mono if it's in front of oxide, because otherwise it would just sound super weird. So that's something that you'll get used to. So let's give a couple a try. Again, I'll give you a few seconds to pause the video. All right, here are the answers. Dihydrogen monoxide means 2 hydrogen, 1 oxygen. So that is H2O. Carbon tetrachloride means 1 carbon 4 chlorine. So that's carbon and 4 chlorines. And you'd indicate that like this. Now, no, this is an example of where mono is not included on the first element. It's not monocarbon tetrachloride. That wouldn't be horrendously wrong. It's just not there. You're never going to hear a professional chemist refer to this as monocarbon tetrachloride. Trinitrogen pentoxide. Tri is 3, penta is 5. So this is 3 nitrogen, 5 oxygen. 3 nitrogen, 5 oxygen. Note, it's not pentaoxide, it's just pentoxide. So this is an example of that second kind of rule thing to remember that I gave you was oxide is a great example, but there's some others where you do it too, where if keeping the last vowel of the prefix would just sound super weird, you drop that vowel. Now, dihydrogen, dioxide, 2 hydrogen, 2 oxygen, 2 hydrogen, 2 oxygen. There you go. Now, what if you have to go the other direction? Well, you're again just going to name the first element and insert a prefix for how many are there in front of that. Then you're going to name the second element, but change the ending to "ide" and use a prefix to indicate how many of that are there. So I'll give you a couple of seconds to pause this video and try these examples. And here are the answers. The first one is 6 carbons and 9 hydrogens. Wow, that's not an H. 6 carbons and 9 fluorines. So it's hexacarbon nonafluoride. The second is 2 nitrogens and 1 bromine. So it's dinitrogen monobromide. The third is 4 sulfurs and 5 iodines. So it's tetrasulfur pentaiodide. And the last is 8 nitrogens and 7 chlorines. So it's octanitrogen heptachloride. And that takes care of covalent compounds. 2 down, 1 to go. We've got to talk about acids now. And there's 2 different types of acids, and these follow kind of different naming conventions than ionic and covalent compounds. The 2 types are binary acids and oxyacids. A binary acid is an acid composed of hydrogen or some number of hydrogens and one other element. An oxyacid is an acid composed of hydrogen or some number of hydrogens and a polyatomic ion. And that polyatomic ion is going to contain oxygen, which is why it's called an oxyacid. We'll talk about binary acids first. Actually, we'll go over this first. The way to remember what to do, the easiest and best way that I can advise you is to think about the anion in the acid, basically the thing that is not hydrogen, and think about how that word ends. And that's going to tell you what to do in terms of naming, as long as you remember these three key phrases. 3 key phrases. My ride has hydraulics. Sprite is delicious. And what I ate made me sick. And the things that are highlighted in red there are highlighted for a reason, which will become clear in just a second. If you're dealing with a binary acid, you're going to use the framework shown here, hydroblankic acid. And what goes in the blank is the root of the anion, the thing that's not hydrogen. So in the case of hydrogen and bromine combining together, that's hydrobromic acid. He took the root of bromine and put it into that blank, and it made hydrobromic acid. Now, the reason that you knew to use this framework is because my ride has hydraulics. The anion here is bromide, right? This is hydrogen and bromine bonded together. And remember how I said acids are kind of like special ionic compounds? So it's a hydrogen cation and a bromide anion. And if it ends in "ide," then you use the phrase, my ride has hydraulics. And I just wanted to throw my an image of my car in here because my ride does actually have hydraulics, and I'm pretty proud of it. I just wanted to show that off. And if you're wondering, yes, I did all that work myself. I'm a pretty multi-talented individual. All right. Now, oxyacids. An oxyacid is again an acid containing hydrogen and an oxyanion, or a polyatomic oxygen-containing ion. This is very different than anything that's come before. All you do is you take the name of the oxyanion and you change the ending. But the way that you change it depends on how it currently ends. So if it ends in "ate," you change the ending to "ic." If it ends in "ite," you change it to "us." And then you're going to add the word acid because it's an acid. And all acids have the word acid in the name. Kind of makes that easy. So for example, if you have hydrogen and sulfate, that is sulfuric acid, because you're going to take the root of sulfate, which is sulfur, and you're going to change the ending. And since sulfate ends in "ate," you change it to "ic," and it becomes sulfuric acid. You might also be asking, why 2 hydrogens? Why not just 1? Well, that's because, again, remember, these are kind of like special ionic compounds, and sulfate has a -2 charge. So that's going to take 2 hydrogens with a +1 charge to make a neutral compound there. So here's where those two phrases, Sprite is delicious and what I ate made me sick, make a little bit more sense. When the anion ends in "ite," you're going to change the ending to "us," and that's how you solve your acid naming problem. And if it ends in "ate," you're going to change the ending to "ick," and that will solve the problem for you. So let's give a couple a try. I'll pause for a few seconds. You can pause the video and try writing some formulas and writing some names. Okay, I'm going to pull the answers up right now. The first example is hydrochloric acid. So that's obviously a binary acid, which means that it's hydrogen and one element. And you know that it's chlorine because the root of the element name is right here between hydro and ic. So it's hydrogen and chlorine, HCl. Phosphoric acid does not start with hydro, so it's not a binary acid, and it ends in ic, which means that it must have come from a polyatomic ion that started or that originally ended in ate, because what I ate made me sick. So if it's phosphoric, it's phosphate. And if you look up phosphate on your polyatomic ion list in your survival guide, phosphate is PO4. And phosphate has a 3 minus charge, which means that it's going to take 3 hydrogens to bond to that. Sulfurous acid. Well, it ends in OUS, OUS or us, and that means that the original polyatomic ion that contains must have ended in ite, because Sprite is delicious. So it's sulfite. Sulfite is SO3, and SO3 has a 2 minus charge, so it's going to take 2 hydrogens, and that's why it's H2SO3. If you encounter HF, that is a binary acid. Obviously, it's only hydrogen and one other element. So you're going to use the framework hydro blank ic, take the root of fluorine, drop it into that blank, and it's hydrofluoric acid. HNO2, that's obviously an oxyacid. So you're going to have to find NO2 on your chart, find the name of it. It is nitrite. And since Sprite is delicious, you're going to change the ending of that to us, and it becomes nitrous acid. And then the last example, CO3 is carbonate. And since what I ate made me sick, you're going to have to change the ending of that to ic, and it becomes carbonic acid. Now, here's the big question. How do you keep all of this straight? Because there's so much that I just threw at you and so many rules that you use in different contexts, but they all are so easy to confuse with each other and to all run together. So how do you keep it all straight? This is kind of the key problem that I always see students struggle with. A lot of students know all the rules, but they don't fully know when to use them. And so when they're trying to name an acid, they'll start using the ionic compound rules. And when they're trying to name a covalent compound, they'll start changing things to ic and us, and it gets all mixed up. So here is how my mind works and what I usually show to students, and I hope this helps you out. Now, I apologize that I haven't had time to put these into a virtual format. This is just a picture of me writing it out on a whiteboard, but hopefully it still gets the message across. The way that I would advise you to think is that you've got 3 different situations: ionic compounds, covalent compounds, and acidic compounds. And you've got to just kind of fragment your mind into those 3 different sets of rules so that you don't mix them up. And you have to form in your mind pathways so that you know when to go down the ionic compound pathway, when to go down the covalent compound pathway, and when to follow the acid path. And what tells you, again, going back to one of the first slides that I showed you, what tells you what path to follow is what the compound starts with. So if the compound starts with a metal, and for example, this is showing you what to think about when you're looking at a formula. If the formula starts with a metal, you're dealing with an ionic compound. So you can immediately forget about prefixes. You can immediately forget about Sprite is delicious and what I ate made me sick, and just think about ionic compounds. From there, you can think, does it have just 2 elements or does it have more than 2 elements? If it's only 2 elements, it's a binary compound. And all you're going to do is write the name of both of the elements, but change the ending of the second one to "ide." Now, if there's more than 2 elements, there's got to be a polyatomic ion in there. So you're going to have to look up the name of that polyatomic ion. If the formula starts with a nonmetal, you're dealing with a covalent compound. So you're going to follow the same rules as ionic compounds, but you're going to use prefixes. If it starts with a hydrogen, you know that you are dealing with an acid. And there's a couple of what's the word I'm looking for? Exceptions to that rule. For example, water, H2O. We don't usually consider that to be an acid, even though it starts with hydrogen. And that's because it is basically, one way you can think of water is it's an H plus and an OH minus stuck together. H pluses, or the ability to give H pluses into a solution, are what makes an acid, and the ability to give OH minus ions into a solution is what makes a base a base. So, and water is basically exactly what makes something an acid and exactly what makes something a base stuck together, which is why it's neither. It's exactly neutral on the pH scale. That was a tangent about water, but hey, my name is Mr. Lake, and I got to educate people on the properties of water whenever I can. So if it starts with hydrogen and it's not something like water or hydrogen peroxide or something like that, then you're dealing with an acid. And if it's only 2 elements, it's a binary acid. So you're going to follow the hydroblank-ic acid format. Remember, that's also because the anion ends in "ide," and my ride has hydraulics. Or if it's more than 2 elements, you must be dealing with an oxyacid. So you're going to find the name of the polyatomic ion and think, Sprite is delicious, and what I ate made me sick. And you're going to change the ending of that polyatomic ion based on those rules, and then you've got your acid name. So again, you're going to just follow the pathway that makes the most sense. And you got to keep those paths separate. And you can think pretty much the same way for going from names to formulas. If the name starts with a metal, you're dealing with an ionic compound. If the name ends in "ide," it's a binary compound. If it ends in "ate" or "ite," that means it's got to contain a polyatomic ion. And so you're going to have to look that up on the polyatomic ion list. If you see prefixes anywhere in the name, you're dealing with a covalent compound. And those prefixes are very simply going to tell you how many of each element are present. And if you see acid in the name of something, then it's an acid. Kind of hard to miss that one. And if the acid starts with hydro, you're dealing with a binary acid. Only binary acids should start with hydro. If it doesn't start with hydro, then you're dealing with an oxyacid. And so you're going to have to just take those rules and kind of go backwards and figure out what the formula is for those things. So there you have it. We're not going to get into that right now. That's the next video. That's everything you need to know about writing ionic compound names and formulas, writing covalent compound names and formulas, and writing acidic compound names and formulas. So I hope that was helpful. And until next time, peace.